based on something called linear approximation. So I know that if I'm only moving not far away from this operating point, a simple way of projecting what happened is to find out di. So what I can do actually is to find out the slope at this particular point. So I can find out di dv at, if I'm projecting this using a linear model, then the slope will then give me, so I'm just going to get the slope and then find out, use a linear model instead of what is the linear relationship between current and voltage, just by using a resistor, because the resistor will project a linear relationship. So the slope will simply be 1 over R. So linearizing it through a simplification of a small signal resistance to linearize this response. So let's take a look at how to do that. So if you look at the current, my total current, if I'm simply, without doing any approximation, I'm simply writing down the corresponding current through this equation, this will be IS without any approximation yet. The specific explicit response will be VDQ plus a small signal part, right? And then minus 1. So that will be my overall diode current under the DC plus the small signal changes. So what can be done is that you could ignore this, of course. And then what we do is that this component is IDQ plus ID. Remember, this is by definition because there's the DC component and AC component. And on the right-hand side, when you ignore this, this will be IX exponential VT VDQ times exponential. I could separate whatever's inside the DC and AC component out, right? So once again, this is the DC component. This is the AC component. I'm separating them out. Okay? So I'm ignoring the minus 1, assuming that you're having a large enough current. And then this will be approximated again. So this would then be this. You simply ignore the minus 1 in all the following analysis. So this would simply be what? Close to IDQ without the minus 1. Because minus 1 is IS. IS is exponential minus, is 10 to the minus 16 something, like less than femtoamp, so you don't actually care. So this is actually equal to that. This is approximated by IDQ. Right, so your equation will be something, this is approximately IDQ exponential. So the first exponential part will be IDQ, and then times exponential VD over VT. Okay? And now we're going to do the small signal approximation. So what is this small signal approximation? Is called the SS approximation. So make sure that you understand the assumption of SS approximation is that when VD VT is smaller than 1. So if I'm assuming that my voltage level, for example, we know that VT is 26. If it's less than 10, we typically typically can accept, even though I said small. But in typical operation, if it's less than, or maybe 10, maybe just half less, we can still use small signal approximation. So the small signal approximation, basically, this has to be smaller than the thermal voltage. So when it's smaller than exponential, your exponential x can be approximate Taylor expansion. There's a higher order, you ignore all the higher order term, and then approximate by 1 plus x. So that's the linearization, or you can do the derivations the same. So then this equation will then become IDQ 1 plus VD VT. This is X, right? Correct? So this is your expression. You're approximated by this. So my overall equation, let me rewrite it again. So I will be arriving at IDQ plus ID equals to IDQ plus IDQ. Okay? So I'm simply rewriting the left-hand side, right-hand side. So I could get rid of the IDQ. I already know that they're all biasing at the same IDQ. I'm only interested in the increment of current. So the increment of current can then be rewritten as ID equals to IDQ. So you actually get the relationship. This is actually what we want. We want to know that if I'm doing a small little change, what is the corresponding small little change in current? So if I'm defining, if I want to find out the equation, so the small signal model of a diode, if it's subject to small little voltage corresponding current, can be equivalent to a resistor RD. So you're simply getting the relationship. The RD should equals to VD divided by ID. So based on that equation, it'll be VT divided by ID. Okay? I miss a Q. So what does this imply? It implies that once I set my operating point, my RD will be fixed. RD will simply be a function of where you stand. This is called the biasing current. Okay? So on this particular plot, you will see that this will actually give us some idea. If I'm drawing this as that, ID as a function of VD. So you will expect that if I'm standing, it will depend on where I stand. This is very important. The small signal response will depend on where I stand, meaning the operating point. So if I'm operating here, for example, this is IDQ1. If I pick this point, the slope here will then reflect in RD1. Right? If I'm standing more to the right, biasing at a, I'm using current biasing. This is very commonly used. Instead of having voltage biasing, you can set it by current. So if I'm standing right here, so this is IDQ1. So the slope will then give me the inverse of the slope. 1 over the slope is 1 over RD, right? So if I'm standing here, IDQ2. So the slope, inverse of slope is 1 over RD2. So the question is, which one is larger? Which resistance is larger? RD1 or RD2? Which one is larger? Yellow or blue? Yellow, correct. Resistance is larger, meaning that, so RD1, because it's inverse proportional to biasing level. So RD1 is larger than RD2. because I dq1, the higher your biasing current, typically the resistance is smaller because of the exponential nature of this device. Okay? So this will be very important when you set your point, depending on whether you want a larger small signal resistance or larger small signal resistance on a diode. So it will depend on the biasing point. Once again, I want to set it at is depending on your biasing current to set the resistance levels. Okay? There's actually two ways of describing this, depending on whether you want to treat it as a resistance or conductance. So sometimes you will actually see another parameter is called diode's conductance. So it will be GD. So inverse of that will be the conductance, small signal conductance. So GD will be the complete name will be small signal conductance of a diode at a particular biasing point. Okay? So you can either treat it as a conductance or a resistance. So what we're going to do is actually, once we have already established the model, we're going to do an exercise. So what is the procedure of, the basic idea is that through this particular model, you want to find this, your corresponding output, through this circuit, through this small signal model. So the basic analysis that is, you start with, I'm just going to go through the example so that I get a sense as to what you do. We're going to start by using this particular example on the diode. So let's say if I'm setting up a condition very similar to that. If I'm biasing my diode at a VB of, let's say, 1 volt, and then I'm injecting a small signal on top of it with a Vs, and then it's being connected to a resistor, looks something like this, R1. So what I ask you to find, if I've given you the circuit and giving you this ID, what I actually want is for you to find ID as a function of time. You should be able to find out what is the ID, the complete both DC and AC level of the diode, of the circuit. So you want to find out what is its DC level, as well as corresponding changes to sources, AC signal. So how do you approach that? So basically, what we typically, in this type of analysis, you separate it in 2 stages. One is you do the DC analysis, find the operating point, and then generate the small signal equivalent circuit, and then add it back together. So let's look at what the DC. So you separate it into 2 parts. One is, first we start with the DC. Let me give the diode parameter. So this is the diode. I'm only giving you, I can either give you exponential model or give you the constant voltage model. This also works for constant voltage model. So I'm giving VD on, let's say VD on is 0.8 volt. Okay? So you start with the DC. You only get the DC part. You turn all the AC signal. In DC analysis, we do is that we set AC sources to 0. You set it to 0, whether it's current source or voltage source, you set it to 0. You only respond to DC signals. Okay? So then the circuit will look something like this. Your circuit will look something like this. There's the battery, VB, and then it's being applied on the dial. Did I give an R1? Sorry. Okay. So if this is the model, if I'm assuming that it's applying to 1 volt, we know the diode turns on. So based on the model, this will simply be, based on the diode model, constant voltage model, this will simply be VD on. So we want to find out IDQ at this point. IDQ will simply be VB minus VD on R1. So we already know that the current will be 0.2 milliamp. This is very important. You need to find out where you stand. So you start with the quiescent point or operating point. You start finding out the operating point, and then we do the second part. So the second part is AC analysis. So for the AC analysis, you set DC sources to ground. Now, for voltage source to ground, but anyway, just set the sources to 0. So we're only looking at the AC part. So your circuit will look something like this. This is being set to ground. So you only have this AC signal from the source and being biased R1. So for DC analysis, we're using, this is the constant voltage model. Here, we're going to use our small signal model. Remember, this is, where's my small signal model? I should, instead of having a dial, I already linearize it with a resistor, remember? Equivalent to a resistor. So I'm just going to insert that in here. I'm insert the model in. My small signal model will be RD equals to VT. So first of all, you need to know the level of RD, because we already know IDQ, VT is given. It's known, so that we should be able to find out that here, RD equals to VT divided by IDQ. And this is 26 millivolt, and that's 0.2 milliamp, right? This would then give me 130 ohm. So then your small signal circuit model is very easy, so you could actually get the current. Remember what we're trying to find. We're trying to find ID, corresponding ID, right? So the current, let me redraw these. So your small, let me redraw this again. The small signal, this is called the small signal equivalent. You're only dealing with small signal equivalent circuit. Will be something like this. You start with a V source. This is, oh, I didn't give the level. Sorry. This is 5 millivolt sine omega t. Okay, my equivalent circuit will be this. R1, which is 1 k ohm, and RD, which is 130 ohm. So your equivalent circuit will look something like this. What we're actually aiming at is to find out the current. So this will be very, very simple. Your ID will simply be Vs divided by R1 plus RD, which is, this is 5 millivolt sine wave. There's no change in your signal. It will still be a sine signal. And then divided by 1.130. Right? So then we get our current. The current will be about 4.4 microamp. Sorry. Okay, this is just to show you that how do you approach of getting the ultimate results. So your ultimate response will be our final plot. Final response is total current will be standing at 200. That's 0.2 milliamp. That's 200 microamp plus 4.4 psi omega t. So if I ask you to plot, you should be able to know that it will look something like this. As a function of time, total current as a function of time will be something centered at 200 microamp and then move up and down with an amplitude of 4.4. Okay? So this will correspond to the changes in my small signal input. Okay? So let me summarize as to what you do. You start with a circuit. I give you a circuit, give you a problem. What you do is that you separate the DC component, the DC equivalent circuit and the AC equivalent circuit. For the DC equivalent circuit, allow us to find our operating point. So that the main point of DC analysis is to find, as I said, to set your operating point at, in this case, will be VB in 1 volt. And then this will set your operating point, and then you can come up with the small signal equivalent circuit. So this is only true for I should say this is only true when IDQ equals to 0.2 milliamp. Okay? For example, if I'm changing my operating point. So what if I'm changing VB? So this is for, let's say, if I have a subsequent question. So this is part 1A. So for part B, if my VB changes to 2 volt, I'm just arbitrary. So what do you think the equivalent circuit will be? So you follow the same analysis. If VB is 2 volt, my IDQ should be what? Should be 1.2 milliamp, right? Am I right? Milliamp. So what you do is that if I'm changing my biasing point, I'm changing where my biasing current is, or increase my biasing current if VB changes to 2 volt. So then I'll then get a RD, which is 26 millivolt, 1.2 milliamp. You get something closer. I don't have the number. I just arbitrarily come up with this. But this will then give you something close to maybe 6 times 2, about 20 something ohm. So it'll be approximately around 20 ohm. So you then have a much smaller resistance because, as we said, if I'm increasing my biasing point, my resistance will actually reduces. The resistance, equivalent resistance will reduces. Then it will then lead to a higher. Your ID will simply be Vs divided by 1020, something like that. Okay, so it will be a slightly higher current, small signal current, because I'm biasing at a higher level. Okay, so you should be able to adjust up and down at a different biasing point. It's good. Any questions? I don't think I have time to move on to the more complicated regulators circuits, so I'm thinking about wrapping up now. So if you have any question, you can bring it up, or we can continue next time on discussion as to once we have this model, how do we apply to rectifying circuits and also regulator circuits. So those are the two examples we're going to go through. The regulator circuit will allow us to look at this, how sharp the current changes. It will actually reflect how good the regulator is. And then we're going to talk about, of course, the main bulk of chapter 3, which is the rectifying circuits. What are the components? How do you analyze those? Okay? So doing it through the two different approaches. So we're going to go through the example. This is the example. I'm going to talk about that a little bit. And then, of course, we're going to go to the main part of this chapter. I think one of the key application of diode circuit is, of course, rectifying circuit. So we're going to talk about rectifying circuit. There are basically two types. There's the half wave or full wave rectifier. How does one realize that? What are the concerns? So basically, when we discuss circuits, the basic idea is that we first introduce the basic structure of the circuit, and then we're going to go into analyze what are the key components or key parameters you need to be aware of, and what are the important parameters one needs to understand, how to analyze them, how to design them. So we're going to talk about that. And one of the key parameters is, of course, ripple voltage of, that's the spec. As I said, any circuit has its spec, meaning that what is the target, what is the problem they wish to address, and what is the target level, how do you analyze this target level, and how do you improve that? That's the key in designing the circuit or understanding a circuit. So let me talk about this. So we're going to start by talking about, this is a regulator circuit. So if you actually look at this, this is more we call a regulator. So what it does is that last time I talked about, some of the students asked me, I talked about the key feature of a diode. So there are basically two. One is that it's asymmetric current voltage relationship, and the other is that, make sure that doesn't saturate. Is this good? Okay, so one is that it's a asymmetric characteristic. So we use that in a rectifying circuit. The other thing is that it looks like, when it turns on, it looks like a voltage source. So what is a voltage source? It will just give you a flat voltage no matter what current you need to provide. So it's not necessarily ideal as a voltage source, but it's close to a voltage source. So we use that feature to create a stable DC source. So this is how the regulator is being designed. So the basic idea looks like this. If I'm having an adapter is just a rectifying circuit coming from your power line. So from this adapter, we want to make sure that when it's applied to your phone, for example, you want to make sure that your output is as stable as possible. So basically what we typically do is that we add another circuit. Aside from the adapter, you add another circuit to protect your circuit, protect the charger, make sure that your charger does not overload or having fluctuation too much. So this is the output of the circuit, which is used for charging. So coming in from the adapter, this is the terminal coming from your adapter. So this is, we call it VAD. I'm using AVAD. So if the adapter coming from your power outlet and rectifying circuit, it actually responds to the ripple voltage. We're going to talk about that a little bit, but later. But assuming that this is your input, and through a regulator circuit, you want to make sure that it's much more stable. That's the basic idea of a regulator circuit. So let's look at how does one approach on this problem. So if I'm looking into an input coming from the adapter, the target is 3 volt, meaning that it's nominal value. Nominal value meaning that it's supposedly to be at this particular, at 3 volt. So we want you to determine there are 3 identical diodes. These are identical diodes. So assuming that the diode 3 identical with 3 identical, let me just define it. So I have 3 identical diodes for my rectifying circuit. So you want to determine, you want to go pick your diode. If this is the circuit architecture, you need to go pick the diode, find the diode spec, determine its reverse bias saturation current, or pick the size of your diode so that your output will be so that VL equals to 2.4 volt. Because it's a 2.4 volt charger, therefore you want your output to, the nominal value of your output be stable at 2.4 volt. And second, we're going to talk about fluctuation, as I said, because even though your targeted input is 3 volt, there might be fluctuation coming from the input. So how do you tolerate this? So we're going to talk about if it changes, if it fluctuates a little bit, how does it affect your output? And we're going to repeat that by using a small signal model. So this would allow us to evaluate how well your regulator is and how do you improve on that. Okay? So I want to emphasize once again that total idea of a regulator circuit is to provide a stable output, 2.4 volt, as close to 2.4 volt as possible. That's the main purpose of a regulator circuit. So let's analyze the part 8. Part A, how does one approach that? So so first of all, what is your VL? Your VL is 3 diode voltage, let's say 3 VD. We actually don't know our VD on because this is the exponential model. So VD is the voltage under your particular current. So what is the diode current we will say the quiescent current coming through? This is the IDQ. Because they are identical, so it's 3 times that. So first of all, we need to determine the current flowing through the diode. In this discussion, we're assuming that it's open circuit, therefore we're assuming that this is close to, you're not actually charging it, you're assuming that it's not charging. Charging is a different problem, it's a low loading effect. We're assuming that we're not talking about loading effects. So we're assuming that even though we know that it's going to take on current, we're assuming that the current level is very small. The charge at a low speed. So first of all, we should determine our current because ILO is approximately 0. So that IDQ, your quiescent current should be VAD. And the target output is 2.4 volts, right? Divided by R1. Sorry, I forgot to give you R1. R1 here is 100 ohm. So if R1 is given, we should be able to find out the current level. So this will be 3 volt minus 2.4 is our target. This is what you want to achieve, right? And that's 100 ohm. So the total current will then be 6 milliamp, right? You're assuming, you know that the current should be, there should be 6 milliamp across these diodes. So then we can determine the voltage current relationship. So because this will be 3 VTLN. What is the diode current using exponential equation? Let me write it again. So the exponential equation is ID equals to IS exponential VD over VT. I'm just going to ignore the -1 because it doesn't affect anything. So you just simply reverse that into IDQ IS. Okay? So through that, we should be able to get this equals to 2.4 volt. So we should be able to get our IS as 6 milliamp exponential The VD here is 0.8 volt because 3 diode divided by 3, right? So this will be 800, 26 milliamp. And then we get our current should be 2 times 10 to the minus 16. Yeah. Okay? So this will allow us to go find the particular diode which will suit this operation. So you go pick your diode or draw, if you're doing it in an integrated circuit, you draw the size of your diode, make sure that it will fit this particular parameters in order to get the output at 2.4 volt. That's how the design process goes. Okay? So the second part is a slightly more complicated, is that if there's a fluctuation, remember our target level is 2.4 volt. So now we wanted to, discuss if there's an input fluctuation on your VID. So how does one approach this problem? Let me use a. So we already know that VL, let me write it again, VL equals to 3 times VD. So the relationship between IDQ, so the device is already fixed. I already know my IS, this is a fixed number. Okay? So how do I find if there's a change, if my VAD changes? So if your VAD changes to 3.1 volt. Okay? Let's assume, you can do the, in most of these diode circuit analysis, you typically do it with iteration. Because you can't, how do you find the balance point? It's through iteration. So the basic idea is that I do an initial guess. I guess there's a very little change. I assume that VL is very close to 2.4. So the current itself, IDQ, should equals to, even though it increased to 2.3, I'm assuming that the voltage will be mostly drop on the resistors rather than changes a voltage on the diode, because diode has a relatively high exponential IV characteristic. So I can guess that the output remains relatively stable. And then I'm just going to get the current. The current is 0.1 K. And this current will be 7 milliamp. So if it's 7 milliamp, you go back to this equation, do the iteration, and find out that VL should equal to 3 times VTLN. This is 7 milliamp. Instead of 6, it increased to 7. So what is the corresponding voltage if it increased to 7? So this would then give us 2 times 10 to the minus 16. You use that number, and we get a voltage of 2.4 A12. Okay? So this tells us that my initial guess is not far off, because it's very close. It's not very far away. So what you do is that you go through another iteration, is that you use this. I'm using this number to get my IDQ. And it will be 3.1 minus 2.4. So I'm inserting this number back. This is typically done and divided by still 0.1 K. So you insert a more precise VL, do a correction, and then come back to get the current. So current will be a little bit refined, closer to the real number. Okay? Even though it drops a little bit, but it's not, it's sort of like a correction. So correct from 7 milliamp because you overestimate the current, because the voltage increased a little bit. Even though you expect it will increase, but how much? So we can do this through exponential or natural log iteration. In this natural log will reduce the sensitivity. So then you go back, we use this number, and go back and actually get the numbers. Actually converge close to, very close. So you get, I should say, so I can use this to do another VL equals to 3 times VT ln 6.88 and 1.2 minus 16. And then we get a very close number. So what does that mean? It means that even though you can do some iterations to make it more precise, but this is close enough. So you can end it when it's like within 1% accuracy, okay? So this is how typically it's being done if we do this through iteration. So this analysis tells us that if my delta VAD is 0.1 volt, or 100 millivolt. So if my input changes 100 millivolt, what is the corresponding delta VL? It will become 11 millivolt. Okay? So this is very effective as to what it designed to achieve. This circuit, as I said, this regulator circuit is designed to make sure that even though my input changes by 100 millivolt, it will attenuate the response at your output node. So it will make it less sensitive to the fluctuation on your adapter output. So that's the whole purpose of having a regulator circuit. Okay? So you will see the power of having a diode circuit, the exponential, using the exponential characteristic of the diode circuit to achieve that, because it was more stabilized on the voltage front. It could provide different type of current, even though there's because the main thing is that you're basically having a different loading current. So even though the current changes a lot, the voltage requires to correspond to this current is minimized. Therefore, you will see the less sensitive change. Okay, so this is more like a qualitative description as to what happened, other than just you go through the exterior and you find out what happens. Okay, but the next thing is that the next challenge for designer is that if you deliver the circuit to your boss and he says that I'm not satisfied with the answer because I think 11 millivolt is too much. I want 5 millivolt. So what do you do? Okay, so if you do this through this iteration process, you're actually lacking a sense as to what should I change? What are the parameters? I could change R1, I could change IS. What are the parameters, or what are the direction of further modification goes? So that's why we need this third part, the small signal model, because a lot of people ask me, why do I want to use some approximated model? The approximated model will simplify the problem and then allow you to see things. So we're going to see how does one approach this problem through another way, through another lens, and then you see the direction of where to go. Okay, aside from running around in a circle. So iteration is very hard for us to get a physical sense or intuitive sense as to how the circuit actually operates, or changes when you change certain parameters, I should say. So let's look at through small signal. We're going to do the same thing, the same problem. You want to find the same answer. You're supposed to be very close to answer, but through a different way. So we're going to through small signal model. So in this case, what is your small signal? Your small signal is simply, we view, first of all, you view delta VAD as a small signal, even though it does not change with time, but it's just a small fluctuation. And you might have the question is that it does not actually fit our small signal approximation assumption. What is our assumption? Remember, what is the assumption? What's the small signal approximation assumption? The voltage on the diode should be smaller, VD over VT, smaller than 1, right? So, but this is 100 millivolt. So does it fit? It does not fit, but in a sense, I would say that even though at the source it does not fit, because your voltage is actually applying here, but when you apply across here is much less. So typically, if I said you can use small signal, just use it. So some of the students asked me that even though it doesn't look small at the input terminal, but across the diode, it will fit that requirement. So you will see that later. So we can still view it as a small signal, and we'll see how much error it will bring. It's actually perfectly fitting. We're not saying the source. Let me just, a lot of you look confused. Small signal model says that VD over VT should be smaller from, not VS. Not the source voltage, it's the voltage across diode. Okay, so there might be a discrepancy between the two. So if you're not sure if you can use that, simply just assume it works, and then if there's problem, go back and fix it. Okay, so we'll assume that we can use small signal. Okay, let me rephrase that. So we view delta VID as small signal. So then you can do the small signal equivalent circuit. So we do the small signal equivalent circuit, it will look something like this. I'm only having the small signal, so this will be my delta VAD. And then there's the R1. Then I will then have 3 diodes in series. But I'm going to model them with a resistance, right? So this will be RD, RD. They'll be identical because they'll be identical because 2 things. The RDs are identical because the device itself is identical, meaning IS is identical. The other is that its current is identical because it's in series. Okay. If it's in parallel, you cannot do that. Because they're in series, they're having the same IDQ. So this will be my IDQ. Right? R1. Okay, so first of all, we want to assume that it actually, where is its quiescent point? IDQ is from problem 1. IDQ is my bias rate before it changes with 100 millivolts. So IDQ is 6 milliamp. Therefore, I already know my quiescent, my nominal value or the quiescent point. Give me 6 milliamp. Therefore, I should be able to find RD equals to VT divided by IDQ. So this will give me 4.3 ohm. Okay? So this is, let me say once again, emphasize, this is the operating point. Operating point is always the point where there's no fluctuation. So that's at the beginning, your nominal position. Okay? So once I have that, I know that my delta V out, so this would then give me the small signal input. Let me highlight it. The small signal input is delta VAD, which is 100 millivolt. Your output is delta V out, because I'm only looking at the variation. Okay? So your delta V out, simply from this circuit, it's just a voltage divider. So your delta V out, in this case, will be 3 times RD, 3 times RD plus R1 times delta VAD. Okay? Right? So I know the value is about 13. This is 113 times 100 millivolt. And you actually get 11.5. Okay? So first of all, the observation is that it's very close to, you do it with the precise model. You do it with the exponential model. It's actually very close, the delta V out. Okay, there's little discrepancy, but we don't actually care too much. So that is to say that in this case, your VL, your total VL will be, if I'm following my example, let me use that. So the total signal will be VL, DC level plus a delta VL. So it will be 2.411. Okay? So you do the superposition back, and then you get the same answer. From method 1 and method 2, it should be at least close enough. We know that a small signal is an approximation, so as long as it's close enough, we accept that. Okay? So as I said, aside from getting to the same answer, what does the small signal model provide in addition? As I said, it provides in addition to this iteration model is this. It provides an equation, this equation. What does this imply? As I said, if I'm not satisfied with the 11 millivolt changes, I want it to be even more stable. I want it to be less than, say, 2% or 5% in variation. So how much, so this actually, this analysis allow us to get a very key important parameter, which is, we call the, let me use the, what are the key parameters for a regulator? Called the line, we define something called a line regulation. Line regulation meaning that if my input changes by a percentage, what is the corresponding output? Okay, so your input changes delta VL over delta V in. So that's actually given by 3RD plus R1. Okay? So if I want to make my line regulator is even less or less sensitive to input, what should be done? So you basically look at two directions, is that you increase R1 or reduce RD. So you can actually look at this equation and know the direction as to how to further improve your line regulation. Okay, so there's direction as to what can be done to change this performance. Or you can actually change AID, because this is whatever input you want to take in, you can actually take in a higher voltage to make your current larger, so RD can be larger. So these are correlated factors. As I said, small signal analysis is an approximation, but the benefit or the advantage of doing that is that it provides you with an insight. This is an insight that cannot be seen through iteration operation. Okay? So we're going to use this very often. As I said, in most of the circuit analysis, accuracy is not actually the key. If you're actually a designer, you just use your hand analysis to get a ballpark. Of course, in this class, if you take an exam, we expect some closeness to the answer. But in real cases, there's always discrepancy between actual models and actual device. So this discrepancy allows us to take in some tolerance as to how much error we can accept. But aside from the answer itself, like the 2.411 voltage, this is not the key parameter. These are the key parameters as to how do you adjust your circuit. If you find out that it's not desirable, what are the direction allow you to change to make it move towards the direction as planned, as targeted, okay? So I think that's a very important concept for you to understand what are the keys in if you're actually into a more circuit design area, you should be learning as to understanding the direction as to how one will move or modify your circuit to reach the target as set. Okay? Good? It's clear? I hope I'm moving in a slower pace. So we're going to move on to the big topic, which is the rectifying circuit. So as we already discussed a little bit as to what is actually inside these adapter, is that you're taking a signal that looks something like this. So in an actual adapter, to deliver the three, adapter is a circuit module which, when you plug in the outlet, it will deliver the 3 volt that you want, right? So what typically is being done is that in an adapter system, what it does is this. We know that it takes in an outlet. The outlet input will be something like this. You look at in a time domain, the signal in time domain looks something like this. It's typically 120 volt. That's root mean square. So it means that correspond to a peak level of 170 sine wave at 60 hertz. So there's 2 key components, is that how fast does the signal change? It would determine the cycle of your rectifying need. And of course, the other thing is that the peak level. So once you know that this is your input signal, that's your input power. And then typically we do is that, first of all, these are voltages that's very hard to handle for integrated circuit. So we can actually easier downgrade it into a lower voltage range so that your device doesn't break down. For example, the junction, typically, let me just give you a number. For integrated circuit, typically the junction breakdown voltage is across maybe to the mode, if you're using lower end technology, more we call the legendary technology, it's probably less than 20 volt. So it's 15 to 20 volts, for example. So that meaning that if you just simply give a 170 volt to your integrated circuit, it will not only this, it will actually damage the device, and then there's no rectifying effect because it will allow conduction in both directions. So what we want to do is to make sure that it's actually within our acceptable operating range. So through this rectifying circuit, you're moving to the next level where you scale down your peak level. So through a transformer, we simply scale down, for example, minus 10 to 10 volt maybe. We don't actually, if your final target is 3 volt, you don't actually want to go down to 3 volt just once, because it will, through the process, it will actually take out a little voltage. So you want to keep it to around 10. So I'm just giving a typical number. So what you want to do is that then we're going to typically refer to as the diode rectifying circuit. Use a diode to create a rectifying circuit. So past this rectifying circuit, your signal will look something more like this, depending on whether it's a half wave or full wave. So I'm just going to draw. More efficiently, this will be a full wave. You flip the negative side. It's called a full wave. And it could also be half wave, you're only taking the positive half. So this is called a half wave. Either way. Okay? So the rectifying circuit basically just either flip the negative side or block the negative side. So after this, we're not really satisfied, because even though it goes in the same direction, but it changes from peak level to 0, peak level to 0. That's too much fluctuation for the adapter because you're assuming that your adapter should be relatively stabilized. So as I said, if I'm accepting maybe 3% of variation, so how do I further stabilize it? This is typically through something called a filter. Okay, you just wanted to get rid of the high. If you look at it in the frequency domain, you do Fourier transform of your signal. These are the higher order frequencies. So you want to take out the higher order frequency components and make it flatter. So that's through a low pass filter. So typically it's called a low pass filter. But we're not actually looking in the frequency domain yet, but just to give you a sense as what it actually means. So you do a low pass filter, and then it will look something more like this. And then this will serve as your VAD. This will be the VAD that we're actually putting into regulator to make it more stable. So that's the last stage. We already talked about the last stage of your overall charging circuit, your charger, your battery charger. Okay, so what happened when you pass? What did I do? Give me a second. So what do we expect when we pass this low-pass filter? It will look something more like this. So this is this, and this. So at this level, you're assuming the adapter will look something, your output will look something more like this. You want it to be at a level, let's say if this is the cycle, the peak level, and it drops a little bit, and then it goes like this. So this is actually the delta VAD we talked about. So it might be targeted to a certain flat level, but is subject to certain fluctuation, small fluctuation. You want to make sure that this is as small as possible. So this is typically referred to as the ripple voltage. You want to make sure that your ripple is tolerable for the your regulator circuit so that it will give out stable charging voltage. Okay? So let me try to analyze the key of these circuits. So transformer. So we already know the purpose of transformers is to reduce, to modify your voltage range. Let me write down the function of this. So rectifying circuit is only positive pass. So allow only positive voltage to change. And then this is to stabilize. Stabilize your output voltage further. Okay? So we're not going to talk about transformer, we're just going to talk about these two elements. Diode plus a low-pass filter. That's the core of a typical, we talk the rectifying circuit, typically constructed by two key components, rectifying, and then you want to stabilize it. After rectifying. So let's start with a very simple circuit that we already talked about. It's a half-wave rectifying circuit. So how does one achieve that? We're going to use the half-wave example. Let me use the yellow. Okay? So a simple half-wave rectifier will look something like this. It would then be bridging the input and output. And then we're adding this as a load. It can be a load or simulate a load. Otherwise, there's no way your current goes. So this would be the VN input signal. So we know that by having, assuming this is VD, right? And then this is VL. So what depends on the type of model we're going to use in this analysis. We're going to use just simply a VDON model. So assuming that the diode has a VDON, I'm going to use the constant voltage model for the following analysis. For all the rectifying analysis, we're going to use the constant voltage model. So we know that it actually operates in two modes. Let's review it. If VD is larger than VDON, larger or equal, doesn't really matter because it should be continuous. Okay. So we view it as a fixed voltage. If it's smaller, we're assuming that it's an open circuit. Okay? Meaning that it's open. So the transfer function, we already plot that before. So it will look something like this. VLVN. If you look at the transfer function, it will be something like this. The cutting point will be VDON, and it will be flat because there's no current flow. It's blocking the signal from coming through. And when it's off, and this is when the diode's on, it will follow with a rate of, because there's a fixed voltage drop between the two, so it will follow with a rate of 1, with a slope of 1. Okay? There's no problem with that. Okay? We already have that. So if you look at in a time domain, we already draw the transfer function. So if you look at in time domain, what is this half rectifying circuit? The response, what I actually care is the time domain response. If I give you a sine wave, what is the corresponding response? So the corresponding response, I think we already draw that before. So if I give you, let's say if my input, I'm just going to give an input. Let's say, for example, if the input is given you as 5 volt sine omega t with a frequency 2 pi over t, where your time is 1 millisecond. So if I give you this example, you should be able to draw the plot of the responding output, BL. So I ask you to draw, first of all, find a plot VL as a function of time, of course. And then, of course, the other thing is that percentage. I should say, I don't know whether this defined well. So we want to know that how, during this whole period of 1 millisecond, what are the time where the diode is on? What are the percentage of time that the diode is on? So it will be the on cycle over the total cycle. Total ratio. I want to know how much time is it on? It should be less than 50, we know, but how precisely is this? It will depend on the speed and not the speed, the voltage, the full, I should say the peak voltage of the signal. So let's do that exercise. So first of all, you want to draw it first. So anytime when you draw a time domain characteristic, I would suggest that you draw the input signal first, and then it will refer that to the input signal. So the input signal is, as I said, 5 volt. And then this is 1 millisecond. So this is 1 millisecond. Am I center enough? So this will be my peak level. And then a drop to, this will be a half cycle. This will be the total cycle. Right? So if I ask you to draw V out, we know that your boundary, when does it cut off, is that when does it transition is with this line. So first of all, you draw this 0.8 volt. So we know that it will switch on at this turning point, right? So if I'm drawing my output response, okay, do I have another color? So I'm drawing my output response. It will look flat before 0.8, and it will follow with a difference of, it will follow, looks like this, and then it will be flat, and then it will follow all the way to here. So the difference between the two, there's a small difference. So the peak level, you should be able to highlight the peak level, it should be 4.2 volt. Because the difference between the two is fixed. This is still 0.8. Right? Because we're using the constant voltage model, there's a voltage drop across the dial. Right? This is very important because you need to know your peak level in order to further analyze its ripple effects. So once we have this, to answer the second, you already plot, you answered part 1. So for part 2, so what we want to know is how long is this? So basically what we're asking is that this is the time when it's on. So this will be the T on. And from here to here is the total period, right? 1 millisecond. So we want to know the ratio between when it's on versus the total ratio. So if I give you a simple choice question, if I don't want you to actually do the calculation, I can give you answers like 30%, 60, 90. So which one should you pick? If I give you 3 answers to choose, 30, 60, and 90, which one? No need of calculation. Which one? 30. Yes, of course 30, because you know it's less than 50. So you don't need to do the calculation to make the choice, just simply. But it's not 30 in this case, but just so you know that the definition, you know in that in a half cycle, I should say, in a half cycle rectifier circuit, your duty cycle, the on cycle would be less than 50%, of course. It would definitely be less than 50%. But how much, it will depend on the ramp rate or the speed. I should say the peak level. Okay, so let me borrow 5 minutes to finish this. So how does one approach this problem is that your T on, if you define a small little change, is actually symmetrical from both sides, right? So from this on, if I define this small little time as delta t, and this is delta t on the right. So your T on, we already know that the T on can be written as 1/2 of your cycle minus 2 delta t, right? Over t. So the thing is that you find out delta t. So how does one define delta t? In this sine wave, we know that what defines delta t is that V in equals to delta t, it equals to 0.8 volt. So that gives you 50 sine omega t, omega delta t equals to 0.8, right? So we actually get, you can use this equation, omega delta t goes to 0.16. And then we should be able to get our delta t. You can use linearize your Taylor expansion, assuming that this is small enough, and this is actually x. So we could actually assume that it's approximately, if you use Taylor expansion, sine x is x, right? Taylor, Taylor approximation. Using the first order term, it will be 2 pi delta t over t equals to 0.16. Okay, so you insert that number back into the equation. We actually get this about, so this, the t will actually cancel itself. So you will actually get a ratio about 45%. You can do the exercise on your own, but the basic idea is that how you find your delta t, assuming that this should be short, and then use linear approximation to do that. Or you can get a precise answer, simply use sine wave functions. Okay? So what we found in this analysis, first of all, is that if you think about, I always use the analogy of having water at your home. First of all is that if the water comes only half day, half of the time, or less than half, only 45% of the time. So you don't have stable usage of water. So what is the thing you're going to do? What is the plan? If you don't have, if the water plant only supply half a day of water, so what do? Yes, you buy a tank. So we're going to buy a tank in our next hour. So we're going to talk about getting a tank, because we know that it only comes in 45%. It's not enough. Even though for full rectifying circuit, you still drop to zero. You still drop to no water to use at a certain moment. So you want to have a reservoir. You want to have a reservoir of charge so that when you need to use it, it provides stabilized output as shown on the right. Okay, so you want to have a stabilized, anytime when I want to use it, I would then have sufficient amount of a supply for it to be used. So, okay, good. So let's take a break for 10. And I believe we're sending out quiz sheets, right?